When trying to find a formula for a quadratic function to fit a graph or numeric data, it's helpful to start by finding the vertex. The vertex is usually the easiest part to find, and when we've found the vertex, that gives us two of the three constants, so we're really 2/3 done at that point. In this case, the vertex is at 1, 3. So what I'm going to do is plug that 1 in for h and plug the 3 in for k as a starting point. I'm going to write this as y equals instead of f of x equals because it'll make the next step a little bit more clear. Y equals a, which I still don't know yet, times x minus 1 squared plus 3. So now all I need is to find a, and I'll be done with the whole thing. There are a couple of different ways to approach this. One way, if you're really comfortable with the idea of graphing a parabola using that 1, 2, 3, 1, 4, 9 pattern, one way is to figure out where that parabola would be, or rather where the points on the parabola would be if there were no stretching or shrinking, and try comparing the two. So this parabola opens down, so I'll draw y equals minus x squared with that vertex, right? It would go over 1, 1, 2, 4, and 3, 9 is probably off the graph. So let's just look at this first one. It's sort of hard to compare these because the graph passes through a fractional value there. So let's go to the next one. All we really need is 1 point to determine completely what that leading coefficient is. If there were no stretching or shrinking at all, I would have come down 4. However, the actual graph comes down, it looks like, half of that, which is 2. Since I only came down halfway to where I would have come without any stretching or shrinking, that tells me that my leading coefficient is a half. Or in this case, because the parabola opens down, I would indicate that the leading coefficient is negative 1/2. So I can tell that just by examining the graph in comparison to the graph of y equals x squared or the graph of y equals minus x squared. However, if that's not a totally comfortable method for you, there is another way that's a little bit more computational, and that has to do with finding another point on the graph and plugging it in for x and y. Here's what I'm going to do. I'm going to take this same point that I just used. This is at 3, 1. And I'm going to plug that in. That's x equals 3, y equals 1. It's a little confusing that the vertex is 1, 3 and this point happens to be 3, 1, but we'll work with that. So I'm going to take this point 3, 1 and plug it in for x and y, and then solve for a. So that looks like this. 1 equals a times 3 minus 1 squared plus 3. 1 equals a times 2 squared plus 3. So 1 equals, let's go ahead and subtract that 3 from both sides. We get negative 2 equals a times 2 squared is the same as 4a. These are gone. And dividing both sides by 4, sure enough, I can see that exact negative 2 over 4 that I was seeing on the graph when I examined it. And this gets me that a is equal to negative 1/2. I do have to express a final answer. I can't just solve for a and then stop. I now need to rewrite my whole function using the values I've found for a, h, and k. So this is f of x equals, my a I decided was negative 1/2. X minus h is x minus 1 quantity squared. And then plus k is plus 3. And I have a function from a graph. You can see the analytic approach where we just look at the graph is much quicker You can get to where you can glance at a graph and very quickly tell its whole formula without any computations. But this other method is a good backup method. This next example is going to be very similar to the process that we followed for a graph, but we're doing this for numeric data instead. This is an application in which the revenue is calculated from the number of cars sold. You can see in this application that selling more cars doesn't necessarily make you more money because this is a supply and demand model. We assume that if you sell 7 cars, you had to reduce the price quite a bit in order to sell that many cars, right? So there's a point at which selling more cars actually starts to bring you less money because you're practically giving them away, right? What we want to do is the same idea as what we did with the graph. Start by finding that vertex, and I find the vertex by looking at the y values. I should find either a highest or a lowest value, and here it is, 20,500. I can see that it gets smaller if I go either direction from there, so that's a maximum. That's my vertex. I also see the symmetry. As I go to the left and the right of this vertex, I can see that I see the same numbers as I step the same number of steps in each direction. So all of those are clues that this is the vertex. Again, I now have y equals a times x minus 5 squared plus 20,500. And I now have to focus on finding a. Much like what we did with the graph, we can, with our numeric data also, examine what would happen if this were just y equals x squared or y equals minus x squared with only shifts. This is an increase of 1 in the x direction, so I would expect to see my y values increase by plus or minus 1. And it looks like instead they go down by 100. So already I can tell that my leading coefficient has got to be negative 100. I can verify that now by seeing what happens if I go 2, right? I would expect to see this, if the leading coefficient is negative 100, this should go down 400. Because of that 1, 2, 3, 1, 4, 9 pattern again. And in fact, it does go down 400. So I have correctly identified the leading coefficient. But again, if I'm more comfortable with a process that I can follow, just take any point other than the vertex as your x and y, plug them in. We get 19,600 for y, and we get 2 for x. Plug them in and solve for a. I am going to subtract 20,500 from both sides. This gets me, I think, negative 900. And over here, these terms are gone, and I have a times negative 3 squared. That negative 3 is inside parentheses, so the whole thing gets squared to positive 9. And that becomes 9a. Dividing both sides by 9, we can see our negative 100 just fall very naturally out of the computations. And again, my final answer is going to have a function with these values filled in for all of the constants. Actually, this one's a little bit long, so I may need to buy myself a little more space to write it. We'll write it down here at the bottom. F of x equals negative 100 times x minus 5 squared plus 20,500.